Welcome back. So, in previous lecture we discussed briefly about the importance of active fault mapping, and we also discussed that in the areas where we do not have the historical information of about the earthquakes or the active fault, then in those areas it is extremely important that we use high resolution satellite data and carry out the active fault mapping and related or associated landforms. Now, this was the last slide where we stopped, and I was explaining that you have the net displacement along the fault. So, this line in section will we term that as an fault plane, and the manifestation on the surface what we see, the topography developed because of this displacement, has been termed as fault scarp. So, similar deformation will be expressed on the surface when there is a displacement along any particular fault. So, this is the case, clear case of the reverse fault, because if you have the horizontal layers, so this I will keep on repeating so that you keep on having the understanding of that. And if you deform or displace this deposits along a fault plane here, then you will be able to see a topography which has been coming up on the surface, and you have the displacement of the layers. So, for example, you have A and B here, so this will be your B and this will be your A. So, further if we see what is the basic idea for this lecture is that we will give you a glimpse of different faulting environment. However, we are going to discuss in detail of different tectonic environment as we move further in this course. Now, the surface expression, the recent one is the 1995 Kobe earthquake, and the rupture you can see over here, which was oblique slip. So, it has a component where if we draw this, then what we can make out that this was having a sort of a reverse component. So, if I am able to draw the sketch here, then what you see is that there is a there's a block here, okay, which has moved up along an inclined plane here. So, this side, so we have basically another block has moved over here. So, the block has moved in this direction along this one, okay, and also along the depth. So, more clear pictures you will be able to see in the next one. So, this earthquake 1995 Kobe earthquake was one of the largest recorded earthquake in Japan and resulted into massive damage. Now, the best way what they did to make aware the people, I'll show a couple of slides in this what they have done. So, this was the rupture of 1995 Kobe earthquake, where you had this side was this moved up, this was down, and then you had a lateral displacement. So, if you can mark this one here as two lines, then you can see the displacement has occurred here, and similarly which was also been observed along the compound wall of this house. Now, what they did was that they they preserved this whole rupture and came up with a museum. So, this whole area, this house was been taken up by the government and this whole area was preserved. So, now what you see is the next slide is the photograph from here, and this whole portion is under the museum. So, this is the wall, and this was the house which I was showing, which also they have preserved the deformation as well as the destruction which was experienced by the compound wall in this house. This house was just sitting close by the fault line, so that did not get damaged or destroyed, but of course the internal damage was huge in this house also because of the ground acceleration. Now, if we quickly look at the configuration of the Japan, I just want to give an idea, overall idea that why this part is important to understand, because after this earthquake, that is 1995 Kobe earthquake, the active fault mapping in Japan was intensified, and they have come up with a digital active fault map of the entire Japan. So, on the global scale, if you look at, then you have the Philippine plate subducting below the Eurasian plate, and you are having the Pacific plate which is subducting below the Philippine plate, and as well as it also having an trench, that is subduction, which is going on between Pacific plate and North American plate. So, Japan lies on two plates, that is, one is Eurasian plate, and in the northeastern side it has it goes into the American plate. So, it has a very complex tectonic framework on the global scale, and on regional scale lot many faults, active faults were been identified, which was been taken up after the Kobe earthquake. So, details of this, if we go further, then this is what they have, the Honshu mainland, one of the main island, and the Kobe is located here, which is very typical of the Bay Area region. And in Japan, if you take the land which is available to this country is very less, whereas and most of the regions, what they have done is they have reclaimed close to the coastal region, because there is an island, complete island chain, and the very less amount of land for urban development and all that is available. So, most of the regions where they have the major cities are either reclaimed or they have modified the landscape and they have constructed those cities. So, Kobe is again in the Bay Area, where you have the part of that is been reclaimed. So, in such regions the secondary effect because of ground shaking will be extremely high, and that what was been experienced during 1995 Kobe earthquake. The rupture, we will definitely learn about the topography of the active fault, but if you see the sharp topographic boundary between the rugged terrain and the flat terrain, it lies somewhere here, and that what marks the fault. So, this is an Awaji Island where the rupture was evident, and we have, this is what we have, the Osaka Bay, and the Kobe is located along the Bay Area. So, you have, this is the major fault line, which is again strike slip deformation or transform fault system. You have median tectonic line, and the earthquake which was triggered in 1995 was at this point. This was the epicenter, and the rupture propagated on either side. So, they had ruptured towards Kobe, and they had ruptured crossing the Awaji Island. So, this was the reason why Kobe faced extensive damage, and this fault which is crossing the Awaji Island was named as Nojima fault. So as if you see here, this is the connecting bridge which was been constructed, which lies between these two islands, Honshu Island and Awaji Island, which also was affected during 1995 Kobe earthquake. And other than that, the damage which was experienced in Kobe was massive. So you can see the flyovers were toppled down, and later they came up with the retrofits and all that. So this was the damage pattern, but and more you can search and Google out, and you will be able to see the damage pattern. But most important for us is the rupture, surface rupture. So immediate after the 1995 Kobe earthquake, the rupture was been identified, and the major displacement was observed in Awaji Island. And these are the signatures. This is an aerial photograph of the rupture, which you can see here, displacing the agricultural fields. Close up of that. So you have. So I'll come to this photograph in coming slide. So you have the movement along the fault. So whatever we were talking in or we have seen in sketches which I was drawing, and what we have learned in the some cartoon clippings of that, how the faulting will take place and which block will move up and which block will go down. So in this case, looking to this photograph, immediately we can make out that this block has moved up and this is down. Okay. And since we know that the mechanism of the faulting in this region was oblique slip, so this was very evident. So there was oblique slip, and the movement was along the fault plane, which moved, resulted into the reverse faulting, plus you had a right lateral movement. So this was the combination which resulted into the oblique slip movement. So reverse plus right lateral, you had the movement here. So this you can easily make out. So you are having the surface rupture coming right up to the ground, and formation of the shear fractures along the fault line, and you can easily make out the displacement over here. So this is the boundary here, and this boundary has been moved like this along this fault. So this portion exposed the fault plane, and this was the fault line. So you have the vertical section, you will be able to see the fault plane, and on the surface this plan view is your fault line. So this was the fault trace which was been picked up after 1995 Kobe earthquake. So this is a close up of that. You can see the displacement here, and further close up, if you see the contact here, that is this portion. The next photograph is of this one here. You can easily make out what we call the slicken sides. So this we discussed in one of the lecture. So this block has moved this side, and all these striations are basically in this direction. Okay. So the movement was along the strike itself. Now coming to this one, this what I was talking, that this block is up, this is down, and if you put the demarcation here, then this portion, okay, of the boundary of the agricultural field has been displaced. Okay. So you have this one here which goes one here. So this is you have the lateral displacement of this one. So you have the upthrown, that is the slope was about 1.9 meter right lateral, and 1.2 meter southeast side was up. So this was 1.9 meter, and then this was 1.2 meter up. So, few more examples which shows the displacement and the fault trace over here, close up of that. So, you have clear cut right lateral displacement which was been picked up. Now, along with this you also had some ground fracturing or the cracks which were developed, and this was associated with the liquefaction phenomena. So, secondary effect will always be seen in the region associated with the strong ground shaking. So, this was the case of liquefaction. Now, as I told that this house was been taken into the custody of the government, and it was preserved. Along with that, this whole area was been preserved, and they came up with a museum. So, idea was to make the people aware that what exactly happened during an earthquake. So, this is a very strong outreach program which Japanese governments usually ask the scientific community to do, and this rupture is been one of the preservation of this rupture and construction of museum is one of the example. So, you can see the right lateral shift of this. So, it has been shifted like this, okay, and similarly you can see the outer boundary which is coming. So, the fault runs somewhere close to this, that is over here. If I precisely draw it on the Scarp itself, so you have it goes like this here, okay. And the displacement is this block has moved in this direction, this has moved in this direction. So, what we see here is the lateral movement along the strike of the fault, whereas the vertical displacement you can see in the next slide. So, there is a close up again of that, and you can easily make out that along with the lateral, this block has moved down. This is a compound wall which was straight, now it is sitting down here, okay. So, this is the vertical displacement between the two, okay, between the two blocks, okay. And this is the side view of that, which clearly demarcates the lateral shift, and this is the in the vertical section you see this block is up, this is down here. Similar photograph from the other side. Now, what they did was they preserved this whole area, and let's see what they have shown in the museum, okay. So, this is the museum right now, and this portion of the part of the museum, the house is somewhere located in this side, and this portion is from this area. I will just show that, okay. Yeah, this is the entrance of that, and then you get into the museum here, and then you see the house on the next. So, that museum which you see here, the building is from that part. So, this road was the old, and now they have completely modified this whole region. So, if you enter into the museum, then this goes as a part of the museum. So, what they did, or they had this rupture, so they dug this portion to put it in such a way that you have the so this photograph is during the construction which was going on. So, they open up the trench, they excavated the section, and they put the glass over here to so that the people can see the contact between the two blocks of different rock types, and the displacement which has occurred. So, you have the displacement. This is the fault plane which is high angle. So, again we will say that this is a reverse fault, and then we have the displacement which is took place here right laterally, which has been shown in other slides, okay. So, so this portion was completely preserved for in the museum. So, liquefaction and lateral spread were experienced in the reclaimed areas mainly near the Kobe, as I was talking, that most of the areas if you see around the bay regions are been reoccupied or areas by filling the sand and the material there, and those areas were extremely got affected because of the strong ground shaking. Associated landslide is another phenomena which one will experience other than the liquefaction. Now, coming to the surface manifestation of earthquake. Okay. So, this was an example of 1891 magnitude 8 Nobi earthquake, again coming from Japan. Now, as I mentioned in one of the lecture that the human memory is of course very short. Okay. So, we keep forgetting the things which have happened in the past very quickly. So, the new generation come up and they will also will not be much bothered, because the time interval between the major earthquakes will be more than 100 years or 200 years. Now, this is one of such example from Japan, where people did not recall or remember, because no earthquake was been experienced in last 200 years or so. So, this is in fault scarp which was mapped and photographed in 1893, and this earthquake was 1891 Nobi earthquake. So, you can see the fault scarp over here. So, this block is up, this is down, and this portion which you see here, okay, I will just put the line here so that it is clear. This is your fault scarp. Now, what happened over the time? Let us see that. Okay. So, surface manifestation of 1891 Nobi earthquake. So, erosion and modification, okay, of the fault scarp created by 1891 Nobi earthquake. You can see that modification has been done, and this photograph was again taken at the time of the just after the earthquake, but later in 69. Okay. In 1969, the same photograph of the not the same, but the same area was been photographed, and what you see is the modification because of the erosion. So, this will also be in part of the process, because the whatever the surface rupture is been seen on the surface at the time of earthquake will not remain forever. It will be modified because of erosion. Also, it will get modified because of the land use planning and all that. Okay. So, present condition of the fault scarp, you see a lot of constructions have come up, and the fault scarp remains here, and the road crosses this fault scarp in 1974. Further, if you see, then what you have is that you have the fault scarp which runs here, just almost close to this building here. So, this was photographed in 1991 by same geologist in Okada in 1974, and further 1991. Now, the question remains that with the modification and erosion, the modification is by erosion also, as well as by the local people or the town planners, this will slowly obscure. So, it will be difficult sometime to identify the fault trace in unpopulated area. So, if suppose you get an old photographs of this region, and in case of the Nobi earthquake you had in 1891. So, if you are getting the photograph of 1891, then you will be able to trace that fault very easily. But if you are looking at the photographs of say 1991, then it will be difficult for us to some extent, but I do not say that it will be absolutely will not be able to identify. So, usually what we do, why I am pointing out this, is that usually what we do is we try to use old satellite photographs. So, for example, in India, that what we have experienced, that when we use the recent photographs or satellite data, then it was with the total modification and urbanization. Okay. And a lot of construction came up because of the increase in population and people are moving, and slowly this city or the town is growing. And so a lot of modification along with the erosion. But if you use the old data, old satellite data, or any such literature which is available either in the historical chronicles or been reported in a published literature, or any written records are there, that will really help in locating the active faults the active fault signatures have been modified over the time. So this is one of the best example which we can learn from 1891 Nobi earthquake and related fault scarp. Now coming to the reverse fault deformation. So please recall the section which I was showing from the Kobe earthquake, that we have the block has moved up and we have the high angle fault, and this block has moved up, and so this is your so you can show the direction something like this. Okay, this is down, and this remains the stationary wall, or we can say the foot wall, and this is your hanging wall. So again you have a very clear features here. You have fault plane and you have the surface, and in section you can see the displaced layers. Okay. So these are the displaced layer, the marker horizons you can take based on the physical appearance as well as the grain size and all that. This part we will learn later. So at least this you can easily make out. Now over the time this will get modified, okay, and you will have in profile something like this. So you have for example you have the displacement which is taking place at the time of the earthquake, and after the erosion what you will be able to see is something like the topography like this. Okay. So you have the modified topography in field. So I am just drawing this so that you have a better understanding. Anyway, so this block has so after the erosion you will be able to see this type of topography. Okay. So at the time of earthquake you may have the sharp topography, but after the erosion and modification you will be left out with a very gently sloping warped surface, and that is what we require to pick up, and this is termed as the fault topography. So this is another example of the thrust fault system aerial photograph from Japan, central Japan. Now, so what we have planned is that we will give you some lectures on, and particularly on how to use the high resolution satellite photograph and how you will be picking up the different landforms. So with the basic understanding of different faults and associated topography like thrust fault, strike slip fault and normal fault, mostly we will be concentrating, will be emphasizing more on the reverse fault and the strike slip fault, So, will first what we will do in module, we will give you a lecture how to use the high resolution satellite photograph, and as I have been mentioning that you need to use high resolution photograph, but other point which I will emphasize is that you need to use in stereo pair, because even though if you are having very high resolution photograph, the 3D perspective view, until and unless you are not having, then you will not be able to identify the displaced landforms or displaced surface. So, you may, because most of the time what we see in using the high resolution satellite data, the photographs either they are panchromatic, or that is black and white or grayscale you are having, or you are having the colored photographs. Okay. So, in that you will be able to differentiate between the displaced landform, or demarcate the geomorphic boundaries based on the tonal variation. Now, tonal variation you will be able to mark, but the displacement, that is the vertical displacement or the lateral displacement, you will not be able to pick up unless and until you are not having the 3D perspective view. So, if you are having an aerial photographs, then to some extent you will be able to pick up the deformation, but if not, because the aerial photography is going to be in very expensive process. So, it is better to use the high resolution satellite photograph or satellite data. So, I will end up here, and will continue with the next lecture. Thank you so much.